We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Okay, my feet are out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 110 of the Space Rocket History Podcast. And now, Apollo, Early Command Module Design. During 1962, NASA faced three major tasks. First, the mode selection and its defense. Second, keeping North America moving on the command and service modules. And third, finding a contractor to develop the separate landing vehicle required by that approach. For this episode, we will turn our attention to North American and the design for the command and service modules. North American engineers spent the opening months of 1962 at desk, drawing boards, and in conference rooms. Although not all the pieces of the Apollo stack had been defined, the first job was obviously to build a three-manned Earth orbital spacecraft. This Phase A, or Block 1 version, which was already worked out by NASA in considerable depth, still required detailed analysis, precise engineering specifications, and special manufacturing tools. The contractor, North American Aviation, also had to make scale model spacecrafts for wind tunnel test and full-size mock-ups of wood and metal for study and demonstration uses. Now I want to introduce the North American team leaders. First, there was Harrison A. Storms, Jr., and he was widely known as Stormy. He was Vice President of North American and President of its Space Information Systems Division. He was a forceful leader in advanced design and development work and a vigorous decision maker who got things done. He had studied aeronautical engineering under Theodore von Karman at the California Institute of Technology during the 1940s. Subsequently, at North American, he had advanced steadily through the ranks with the nationally famous test pilot A. Scott Crossfield, among others. Storms had shepherded the company team through the first phases of the X-15 and later the XB-70 aircraft programs. Next, we have John Paup, who had worked at North American for several years, then spent a little time at Sperry Rand, and then returned to North American in mid-1961 to help Storms bid on the NASA proposals and to become general manager for Apollo. Paup, in turn, picked Norman J. Riker, Jr. as his chief designer. Riker, who had joined the company in 1951, had been a stress analyst on the Pioneer Navajo missile. He had also helped prepare bids for contracts for the Ranger and Surveyor spacecraft. North American had lost these competitions, but Riker had remained in advanced design work. Charles H. Felts, a company man since 1940, was the fourth major leader of the North American Apollo development team. He had worked on P-51 and B-25 aircraft during the Second World War, and later on the B-45, the F-86, and the F-100. Felts had been project leader on the X-15 rocket research aircraft, coming into close contact with NACA and then NASA leaders with whom he would work on Apollo. Felts was considered by his peers to be one of the best manufacturing managers in the airframe business. Back in the days before Project Mercury, North American, with General Electric, had been under contract to the Air Force for the Man in Space Soonest project. When the Air Force lost the Man in Space flight mission to NASA, North American had put in a bid for Mercury. After losing to McDonnell Aircraft Corporation in 1959, North American officials in 1961 were not eager to chance another defeat in a major NASA competition. But Storms and Paup, after combining forces with Riker and Phelps, were determined to try for Apollo. When NASA picked North American on September 11, 1961, to build the S-2 second stage of the advanced Saturn, J. Leland Atwood, president of the corporation, and Samuel K. Hoffman, president of the firm's Rocketdyne division, were reconciled to this role in the program. Storms, Paup, and Riker were not. They pressed on to win the spacecraft contract as well. Storm's team operated from a two-story building in Downey, California. Design engineers and draftsmen occupied the major portion of the structure. Their desks were crowded together in the cavernous halls. An adjacent building housed the manufacturing activities for the space division. 90% of the property belonged to the federal government, but long-term leases had made North American as tenant virtually the proprietor. Now, with the Apollo contract, plans were made to recruit personnel to build adjoining property and to construct more buildings and facilities. In the meantime, some of the personnel worked out of the house trailer offices in the parking lots. The manpower buildup in the Storms division in the first 6 months of 1962 doubled the size of his organization, from 7,000 to more than 14,000 persons. Although many employees were busy on the Air Force's Hound Dog missile, among other projects, the newcomers, for the most part, were hired to develop the Apollo command and service modules. The Impact Test Facility was one of the first structures built at Downey, specifically for Apollo. Construction began on it in early 1962. The Impact Test Facility was 46 meters high and looked like a giant playground swing. It really was a swing of sorts. It was designed to hold and drop a command module so the Apollo team could study and improve structural strengths of the heat shield, honeycomb shock absorbers, inner and outer shell, afterbody, and astronaut couches. At one end of the swing was a pool of water. At the other, a sand pile that could be banked or pitted with gravel and boulders. To return men safely from the moon required a knowledge of the exact limits they and their machine could endure at the final landing on Earth. As expected, structures, heat shields, and radiation protection were primary concerns during the first year or so. Unexpectedly, however, the manufacture of mock-up modules, initially considered of less importance, quickly grew into a major program to supply boilerplate spacecraft, and by boilerplate, I mean metal models designed to be used in testing. North American Structural Assembly Department had begun tooling up for extensive work on mock-ups in January of 1962. By the end of the year, this shop employed 305 persons on 3 shifts, tooling, drilling, welding, and assembling custom-built units. D.W. Childley, a 14-year veteran of North American's prototype manufacturing and head of the department, reported at year's end that the group had built 6 test vehicles and 2 full-scale mock-ups, which had been featured in NASA's North American reviews during the year. To keep key personnel ready for the frequent meetings with NASA, and aware of daily plant operations, Storms, Paulp, Riker, and Phelps held 10-minute briefings for all plant supervisors at the beginning of each morning shift. Agendas were carefully controlled. No interruptions were permitted, and everyone was required to speak for his section. Thus, until North American's Apollo operation grew too large to make this kind of communication useful, all the major managers had at least one daily direct contact with their colleagues and superiors. You may recall from previous episodes that North American was responsible to subcontract work beyond their expertise. Some of these 10-minute briefings were devoted to plans for selecting and working with the subcontractors who would develop the subsystems. Shortly after the NASA North American contract was signed, subcontractors for 4 of the spacecraft systems were selected. Collins Radio Communications Company for telecommunications, the Garrett Corporation's AI Research Manufacturing Company for environmental control, Minneapolis Honeywell Regulator Company for stabilization and attitude control, and Northrop's Corporation Radio Plane, which was later Ventura Division, for parachutes and earth landing. North American soon added other subcontractors. In February of '62, the Lockheed Propulsion Company was selected to design the solid propellant motor for the Launch Escape Tower. By the end of March, the Marquardt Corporation had been chosen for the Command and Service Module's Reaction Control System. Aerojet General was chosen for the service module's main engine, and Avco Corporation for ablative coatings and spacecraft heat shield. In April, Thiokol Chemical Corporation was named to work with Lockheed on the Launch Escape System. While NASA was trying to decide on the mode during the first half of 1962, John Paulp and his North American engineers were getting restive. Although repeatedly warned by his own people not to bend tin or cut metal too soon, Paulp insisted that hardware production should get underway. He did have his model shops turn out a mock-up of the Lunar Excursion Module, which looks something like a helicopter cab on top of thin, spidery legs, and a Lunar Braking Module, just in case a direct route to the moon was chosen. On the 1st of June, Paulp wrote Houston that schedules for spacecraft delivery were slipping further and further behind. How could they build the service module, he asked, if they did not know what it would be used for? But there was at least one area where work could start immediately. Early in the contract, North American and Houston engineers had agreed on a flight test program, putting boilerplate command and service module through structural test and checking out the abort system. In mid-1961, while he was still with NASA before joining North American, Alan Kellett suggested using a fin-stabilized cluster rocket, solid propellant booster for these tests. The Little Joe 2, named after the Project Mercury test vehicle, would be able to propel a full-sized Apollo re-entry spacecraft to velocities as great as those in the critical portion of the Saturn trajectory and at altitudes of 60,900 meters. The test would be a simple and fairly inexpensive way of determining, in flight, the full-scale spacecraft configuration concepts, system performance, and structural integrity. Test of the launch escape system at maximum dynamic pressure would be most useful and important. In May 1962, the Convair division of General Dynamics was selected to develop the Little Joe 2. For the test area for Little Joe 2, NASA considered launch sites at Wallops Island, Virginia, Eglin Air Force Base, Florida, and the Cape. But the New Mexico desert north of El Paso, Texas, was selected early in the spring of 1962. The Army White Sands Missile Range seemed the most suitable for Little Joe 2 ballistic flights. Selection of Little Joe also completed the Apollo family of launch vehicles, which consisted of the Saturn I, the Saturn 1B, the Saturn V, and Little Joe 2. NASA engineers expected to conduct 3 kinds of tests at White Sands. First, pad abort test, in which a solid-fueled rocket mounted on a tower attached to the top of the command module would pull the spacecraft away, as it would have to do if the Saturn threatened to blow up on the launch pad. The second test would be at maximum dynamic pressure, or max-Q, in which the rocket would pull the spacecraft away from the launch vehicle if the booster veered off course shortly after launch. And the third test would be at high altitude, in which the rocket would haul the spacecraft away from the launch vehicle if the Saturn were unable to boost its payload to orbital flight. Other organizations, such as Ames Research Center, had been working on Apollo while waiting for the mode decision. Quite often, after a day's work at Downey, North American engineers flew to Moffett Field carrying models for Ames to test in its wind tunnels. Ames engineers were also dropping test vehicles on a simulated lunar surface to study landing gear designs and possible structural damage on impact. Ames had a close relationship with its Navy neighbors at Moffett Field. Navy Flight Sergeant Harold A. Smeedle, who had been in aviation medicine for years, was a logical consultant to NASA research engineers interested in physiological instrumentation as well as pilot performance during flight. Smeedle worked on spacecraft cabin designs, especially on cockpit layouts that emphasize pilot convenience in spacecraft control. Another example of Ames applied research that fed into North American was the work of test pilots and life scientists in ground-based simulations of the characteristics of spacesuits, restraint harnesses, work-rest cycles, and isolation conditions. North American and Ames were intent on making certain that the cockpit was designed to take full advantage of the pilot's capabilities in performing and sharing their duties. The Lewis Research Center in Cleveland, Ohio, also took a hand in getting spacecraft development on a good footing by putting Marquardt reaction control jets through a test program. These small motors were used to turn the spacecraft right or left, up or down, or in a roll maneuver. These small motors were cooled regeneratively, and by regeneratively I mean the process in which the expansion of part of the hot gas cools the remainder. When tests showed that the engine would burn up during re-entry heating, Houston directed North American to only use Marquardt motors on the service module, since it would be jettisoned before re-entry, and to make or buy command module jets similar to the ablative engines developed for Gemini. In August 1962, the command module thruster contract was transferred to North American's Rocketdyne division, which produced Gemini altitude control and maneuvering engines and the re-entry control system. Even though the Manned Spacecraft Center had gained its independence and had moved away, the ties between NASA Langley and NASA Houston remained strong, providing another source to draw on for help. Shortly after they moved to Houston, Axel T. Matson came to Texas as full-time liaison officer, coordinating the use of Langley's 5-meter transonic wind tunnel in testing and studying the aerodynamic effects of reaction control jets and escape tower exhaust plumes on the command and service modules. Moving on to Langley and the heat shield, Langley's wind tunnel experts conducted diagnostic tests of heat transfer, heating loads and rates, and aerodynamic and hydrodynamic stability on the command module heat shield. The heat shield contractor, the Avco Corporation's Everett, Massachusetts division, had proposed an ablative tile shield, a layered and bonded single-piece construction similar to that used on Mercury. Then McDonnell had advanced heat protection technology by developing ablative filled honeycomb material for Gemini. When North American and NASA engineers approved this thermal protection, Avco refined the new system to withstand the higher heat rates of lunar reentry. McDonnell's Gemini heat shield was made of a fiberglass honeycomb material. The ablator, developed by Dow Corning, was poured into the honeycomb material and allowed to harden. The Apollo ablative heat shield, however, was bonded to an inner brazed stainless steel honeycomb shield, and the 400,000 honeycomb cells in its plastic outer cover were filled by hand using a caulk gun with an ablator developed by Avco. While the heat shield was going through its growing pains, the Earth landing system for the command module was beginning to mature. Apollo's preliminary plan had included either water or land landing. John W. Kiker, a landing system specialist in Houston, had studied several alternatives: a rotating wing, like a helicopter's, a flexible wing, similar to a paraglider, or traditional parachutes, such as were used in Mercury. Kiker, working with experts at Langley and Ames, ran the proposed models through wind tunnel tests and then asked the Flight Research Center to put the equipment through free flight tests at Edwards Air Force Base. But by the middle of 1962, hopes for a touchdown on land were beginning to fade. At a meeting in Houston on May 10th, engineers of Northrop Ventura, the recovery system subcontractor, described their designs for a cluster of 3-ring sail parachutes for the main landing system. North American liked Northrop's proposal better than the system being tested, which deployed the parachutes through the heat shield cover on the conical top of the command module. In the proposed system, the cover would be jettisoned before the parachutes were released. On May 16th, Houston told North American to go ahead with the development of this multiple parachute system and to set the paraglider aside for further review. You may recall from previous episodes, at that time, North American was developing a paraglider landing system for the Gemini spacecraft. In Houston, Max Faget noted that the contractor was having trouble with the Gemini system, and he became skeptical of the paraglider's value for Apollo. In June of 1962, Faget recommended water landings for the lunar program. At NASA headquarters, George Lowe told Brainerd Holmes that North American's concentration on parachutes for Apollo would mean the end of the paraglider for that program. Holmes wanted to know if it could be put in later, provided the technical difficulties were solved. Lowe said this could be done only if the paraglider were ready within a year. But when NASA and the Navy recovered John Glenn and Scott Carpenter and their Mercury spacecrafts from the water with comparative ease, chances for a dry landing in Apollo grew very slim. Another key part of the command module that NASA had to keep moving was the guidance and navigation system. To get started in the right direction, representatives from North American and MIT decided to meet regularly either at Downey or Cambridge to keep an eye on progress and trade information. In early 1962, the guidance and navigation system had, of course, progressed very little. Some advances had been made on the gyroscopes and accelerometers for the inertia measurement unit, similar to that used to help guide the Polaris missile. But digital computer development and the space sextant were not well defined. Manned Spacecraft Center's engineers had questioned whether an astronaut in a pressurized suit could operate a sextant or the other delicate pieces of navigation equipment. The Apollo contract had specified a shirt-sleeve environment. For this reason, North American had been told not to include in its design a hatch that opened by explosives like Mercury's. An accidentally blown hatch would cause an instant vacuum and certain death for a crewman not wearing his pressure suit. But on some occasions, such as launch, the crew would be in their suits and would need equipment that could be operated while wearing the bulky gloves and helmet. In June 1962, several Manned Spacecraft Center and North American engineers went to MIT to learn how the crew was to operate the guidance system. One of the talks covered the use of the sextant in determining navigational position. At that point, the MIT experts were invited to Houston to try operating the sextant while wearing an inflated suit. Whether they came was not documented, but in the succeeding months, modifications made the sextant and the suit operation more compatible. The chief result of all these meetings, however, was a new understanding of the command module's cabin layout, which gave MIT a clearer picture of how components should fit. Ames Research Center engineers also participated in the meetings, which gave Gilruth another set of specialists to call upon in monitoring MIT's work. The Ames guidance experts sponsored a session at a NASA University conference that dealt with such subjects as mid-course guidance and navigation techniques and the procedures for reducing the uncertainties connected with these operations. Ames speakers recommended making mid-course corrections early in flight to avoid the wider dispersions and greater fuel use that might result from making trajectory changes closer to the moon. Studies by Ames on atmospheric entry guidance, another critical operation, indicated that a man could indeed steer his spacecraft through the narrow reentry corridor to a safe landing on Earth. When some components of the command module's guidance and navigation system were ready for development and fabrication by subcontractors, NASA Associate Administrator Robert Siemens appointed a Source Evaluation Board in January 1962, headed by Robert G. Chilton of MSC, to select industrial supporters for MIT. NASA chose the AC Spark Plug Division of General Motors to build the inertial platform, Raytheon to make the digital computer, and the Colesman Instrument Corporation to manufacture the optical systems. By May of 1962, most of these contractual arrangements were complete. NASA's top officials had been concerned about MIT's ability to build a guidance and navigation system that would take a crew to the moon and back to the Earth. As the system began to take shape, another worry cropped up. Would the instrumentation laboratory be able to manage the industrial contractors once the design evolved into development? To be certain that the subcontractors understood the arrangement, Siemens visited the Wakefield laboratory of AC Sparkplug in July, where he was assured that AC and MIT could work together just as they had on the Titan II inertial guidance system. But the managerial task in the complex and interlocking systems of the command module, as well as those of the other vehicles in the Apollo stack, had to be spelled out in precise and formal guidelines to ensure orderly progress. A system of interface control documents became standard. There was nothing very mysterious about the interface control documents. Somewhere along the line, some piece of Apollo's 2 million functional parts assembled in one place had to meet and match with a piece put together in another place. After MIT had designed and supervised the building of the guidance and navigation system, for example, the component was sent to North American for installation in the command module. Size and location of the equipment had to be defined and agreed upon in advance so it would fit properly. Because of the many companies working on the different parts of the Apollo stack, these interface documents were essential in laying out just where and how the parts would come together. Systems with spacecraft with launch vehicles with spacecraft with launch facilities, and all these systems and crafts with the crew and with the launch and mission control centers. All in all, during 1962, good progress had been made in getting command module development underway. Contractors were working together, and cooperation among the NASA field centers had improved. One of the underlying factors in this advancement had been the establishment of a formal Apollo spacecraft management office at the Manned Spacecraft Center. In January 1962, when Charles Frick became manager of the new Apollo Spacecraft Project Office, he assumed responsibility for the technical direction of North American Aviation and other industrial contractors assigned work on the Apollo spacecraft project. Frick arrived at Langley Field, Virginia, just in time to meet the 45 persons that his deputy, Robert Pyland, had gathered into the new project office before they moved to Houston on February 1st. The new organization settled into the Rich Building, one of the center's 13 rented sites scattered around the Gulf Freeway. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.